Today's electronic products, especially consumer electronics, continue to become smaller and smarter. They contain flex and rigid flex circuits that enable manufacturers to keep form factors small, provide flexibility, and improve reliability by eliminating physical connectors. Many of the products we use today, like tablets, GPS units, smartphones, health trackers, wearables, thermostats, and many more, contain rigid flex PCBs in their designs. In order to successfully design a product with rigid flex technology, you need a PCB design environment with design capabilities that are rigid flex centric. PADS Professional has the design capabilities that both support and guide you through the unique requirements for success in both designing and ensuring the manufacturability of rigid flex PCB designs that other design tools don't have or are limited. To demonstrate how the rigid flex centric PCB design capabilities in PADS Professional helps you create and accelerate modern product designs, I'll turn this webinar over to one of our technical engineers, Brent Klingforth, to demonstrate how. Brent?
Thank you, John. I agree with you 100%. I have a feeling many others listening today do as well, that more and more products are being introduced, or existing designs, depending on the industry, are being pushed to reduce form factors. Flex and rigid flex, in most cases, is the answer. Sectional boards interconnected with flex can be used to wrap electronics around an arced or circular object. Cost can be reduced by eliminating connectors, cables, and assembly steps, or boards can be folded on top of each other when surface area is limited. As John mentioned, there are special or unique design requirements when working with flex and rigid flex designs. As such, not all PCB design tools have the proper design capability, allowing you to design with confidence. Before we get started, let's review some of the special flex and rigid flex design attributes your tool should be aware of for you to produce a high-quality manufacturable design. Trace routing should be done with arced corners. All entry and exit component solder pads and vias need to be teardropped. Use rounded corners on all rectangular or square land patterns. No components or vias should be placed in or near flex bend areas. Traces need to be run perpendicular to bend areas. Do not change trace width or direction in a bend area. And plane areas should be hatched to reduce copper area on the entire flex. Well, let's start out by showing the product that we're going to be designing a board for that's going to be using this flex and rigid flex design technology that we're talking about. So this is a handheld thermal camera. If we go ahead and open up the PCB view of the board, we can show you some of the innards in this. So we've already just got one board down on the bottom. That's an RF module. We have another camera module up here that we need to connect to, and then we have some buttons up at the top. So instead of using cables, we're going to use a PCB. Again, we'll go to another view with some of these items turned off. So here's just more of a plain view of the board. So the mechanical engineer can start out by designing some of the basics for us here. He knows what the mechanical mounting position of the board is. The exterior, he can put in roughly where the flexes need to be. It's like if I turn this on, we can see we have a flex connector here that we need to mount to. So he's drawn in a rough location of where that is. And then we can transfer that information over to the PCB so that we're not trying to do this with drawings. All right. So to do that, it's very simple. We make this a working part here in the NX application. We define the board, any mounting hole locations that we have, and then we simply publish the PCB to our common location of where data is going to be shared between the electrical engineer and the mechanical engineer. Hit OK, and we go ahead and publish this, and then we'll be able to go over to the PCB and import this directly in and start making modifications for some of the overlapping flex areas, defining the flex regions, and working with the bends. So you would think the mechanical engineer would be able to do a lot of the bend stuff, but mechanical tools don't have any of the intelligence built in that we need and that we'll talk about here in the PCB tool. All right, so here's our basic PCB that we've forward annotated our schematic information into with an 8-layer stack up that we're going to be dealing with, at least for the main part of the board. But that's one of the important things that we're going to talk about is how to define individual stack ups for the areas of the board. It's very important functionality that differentiates a basic PCB tool with one that has flex centric capabilities. So we'll start out by importing our board. So as we pointed out earlier, the mechanical engineer has created our IDX file with our collaboration tool between NX and PADSPro in this case, but you can also use SolidWorks, any other tool that supports the IDX interface format. So by clicking on the file, we can see the items that are going to be imported, and then we can go ahead and apply those, and you'll see it will automatically create our board outline for us, mounting hole locations, and all the items that we need to start making adjustments to that the mechanical engineer created for us. So in a matter of seconds, I've brought in my PCB design and flex region areas, saving a tremendous amount of time. All right, so now in this design, we've got a little rigid board up here that some buttons need attached to. So if you remember seeing that in the mechanical, there were 3 buttons sitting up here that the user needs to use to function with the design, but we have to attach to those buttons to get input on the electronics. All right, so that's what this board is here. And then we've got that RF board down the bottom that we're going to connect with the flex. And then we have the camera board that we're also going to connect with the flex. One of the most important aspects in designing any rigid flex or flex circuit design is obviously dealing with the board stack up, and how do we go about doing that? So with PADSPro, we use the Stack Up editor from our hyperlinks application that has additional features added to it for defining flex layers. All right. So the push button board is we're going to route that out from layer 2. And it's only going to be a 2-layer board. We only need a 1-layer flex, actually. So what we need to do is add at least the 1 layer in here. All right. So underneath the dielectric, right above layer 2, we're going to insert a flex region. Right. And right above that, we're going to put a cover layer because we have to. That's like the solder mask, obviously, for a flex. You can add adhesive if you want, but it's so thin. It depends the type of adhesive that you're using, and if you want to take that into account in the thickness of the board. But you can add that layer in as well. And then on the bottom half of the board for the camera and the RF board, we're going to use a 2-layer flex, one with a ground plane on it. So our ground plane is going to be, obviously it's already on layer 6, right? So just above that, I'm going to add again a cover layer, and then we're going to put a separate substrate in here for the flex. And then we're going to add another cover layer. All right. And then each one of those flexes, the camera and the RF one are going into flex connectors. So we need to add a stiffener layer because most flex connectors have to have a certain thickness. And as we know, flex material is very thin. You can range the flex material Kapton from 1/2 mil actually all the way up to 9. But it depends on the flex connector that you're using. So in most cases, they do require a stiffener on there. Okay, so in this case here, we're going to route the traces on layer 7. So the stiffener is going to end up being just above the cover layer on layer 6. So above here, we'll add a stiffener for both of those. All right, we don't need one for our button board because obviously it's gone from one board into another board. So with those layers added, and it would tell us if we had any discrepancies or errors in the way that we've defined this. We don't necessarily right now have to worry about board thickness because for each layer stack that we define, we're going to define the thickness at that level. And you'll see that here in a second. So we'll click OK. All right, so we go back to the setup menu and we have what's called Stack Up schemes. This is where we're going to define the actual individual stack ups for the different areas of the board. So let's go ahead and create a couple schemes here. Our first one will be, we'll just call it button board. And then we'll make another one called RF Flex. And then we'll make another one for our camera flex. And then we'll make another one for our button flex. And we'll make another one for our main board. So now we need to define Stackups for each one of these. So for our button board, we click on this, we can see all the layers that were just defined in our Stackup editor. So I'm going to include the solder mask. I'm then going to include my signal layer 1, my flex substrate. We'll also need our dielectric and then our layer 2 and then solder mask bottom because our button board's only going to be 2 layers. So if we do a stack up view of that, we can see what that looks like. And then this is where we can adjust the thickness of the board. So we're going to go ahead and make this, we'll just make it like 30 thousandths. The board doesn't need to be super thick by any means. We can adjust our solder mask layers, our copper weights if needed. I want the dielectric to be 30 actually, or 20. I want my flex material to be 2. All right, copper weight and so forth. All right, so there's our basic 2-layer board with our flex substrate that a copper trace will go on to. Next, we'll do our RF flex stack up. So we click on that. Easier to turn all these off. And then we can select the stiffener, cover layer, plane, flex substrate, signal, and cover layer. Again, we want to view that stack up so that we can adjust the thickness of items, like the stiffener being 3. This doesn't need to be 10. That's 2. 1/2 ounce copper. This needs to be 2. All right. Again, it'll tell us if we have any violations. So we have a cover, signal, dielectric, signal, dielectric, and our stiffener. And then we'll review some of the other ones like the main board. I've already gone ahead and created these. View the stack up again as normal. You can adjust your layer thickness parameters as needed. So we've done one of the most important parts in designing a rigid flex board, and that is defining our stack up region or Stackups that we'll use in the different regions of our board. All right, but now we need to define what those regions are. So in this case here, so when the IDF data came in or IDX data came in, it came in as individual board outlines, which is what we want to see. All right, so we have our main board here. We can double click on that. I can name this. We'll just call it main board. But most importantly here is I need to set its type. It's already set to rigid. And I can now choose that stack up region or that stack up that I'm going to use for this region, which in this case is the main board. All right. And then we can do this for all the other flexes. So here's our camera flex. We're going to turn that into a flex region, and then we'll choose our camera flex stack up. All right. So the nice thing about this is we can reuse all these over again. So this one over here is using the exact same stack up as the camera flex one. So again, this is going to be flex, RF, flex, so now we've defined all of our regions for our different flex. So this is, again, where the important part comes in. Some CAD tools out there, when you have overlapping flexes like this, you have to define a stack up by each individual little shape. So if I adjust this shape at all, I have to go in and readjust the regions for those shapes, or what stack up is going to be assigned to that. With PADS Professional, it's all just based on a board outline. It doesn't matter if I adjust this board outline or not, it's always going to use that same stack up. So it simplifies your entire process of creating a rigid flex board. All right. So now if we go into 3D real quick, we can see all of these different regions now. So before, when they came in, they were all the same thickness, where now if I look at these, I can clearly see these two coming off on the internal layers, and this one, my button flex, coming off on the top. All right. And again, where they're overlapping here, the tool now knows that these two are not connected to each other. All right. So simplifying the entire process of dealing with your stack ups for your regions. And if I make any adjustments at all to these shapes, I don't have to go in and worry about reassigning any new regions that get created with stack up data. It's already inherently done. Real quick before we move on, I did want to mention some just basic fabrication capabilities of Flex Design from that are probably more common with most manufacturers out there. Materials that you're using, the polyimide materials, can range anywhere from 0.5 mil up to, like I said, 5 millimeters. Copper on Flex can range anywhere from an 1/8 ounce up to 3 ounces. All right. And then your adhesives are generally so thin that you typically don't have to take those into account. Your conductor spacing on a Flex is actually better than a rigid Flex. You can get down to 2 mil, even though I guess you can do that on rigid boards as well. Vias are very small, again, because everything is laser cut with polyimide. So the aspect ratios that you can use on vias is down to 12:1. Unlike rigid boards, it's typically around 8:1. All right. So that's just the couple technical parameters that I wanted to outlay for those that haven't designed a Flex before, things to consider. It's always a good idea to obviously consult with your manufacturer before you start designing a rigid Flex board if you've never done it before. All right, next we're going to move on to adding our bend areas to our board. All right, so by clicking on our 3D tab down here again, we can get a look of our board in the 3D realm. I did import components onto the board and place those here real quick using reuse functionality in PADS. But to assist with the setting up the bending of the Flex, we can tile our windows side by side. That's going to make it a little bit easier to deal with this. So I can tile vertically. Let's close that guy out here. All right, so now I can view the board at the same time I'm dealing with the Flex regions and the bending. All right, so to add a bend region, we simply go to the draw menu, type in bend area. We basically draw a region over the top of a Flex area. It has to encompass both sides, so it's got one side there and it's hitting the other side here. I can then double click on that, and now we have parameters that we can define, and we'll review these real quick. And we're going to play around with a couple of these. So it automatically identified that it was going to associate itself to the button Flex because those are the two edges of the Flex that it crossed over. It's got some default numbers in there, but we're going to adjust those. The bend origin just determines where the bend is going to occur relative to the shape. Bend order, is it being used currently? Now, area tolerance is a neat feature. This allows us to control how close an item like a via or a component can be placed to a bend area. We'll see that here in a second when I play with that. Dynamic bending is there because if we go to our settings for the layout tool, we can define what our minimum bend radiuses can be based on the thickness of the board. So there are specifications generalized in the industry and how much you can bend the flex material based on the number of layers or how thick it is, and, to make it reliable. And if you're doing things like dynamic bending, say like a cell phone or a computer or anything that the flex is going to be moving all the time, or in a mechanical device that the arm's moving around and has a flex on it, the bend radius has to be much larger so that the copper doesn't break. And the tool dynamically is going to verify this. And I'll show you that here in a second. Just with the default set here, I'm going to go ahead and let the tool go ahead and bend this just so you can see it real quick. Go to our display control, our 3D tab, and we click on the flex bend. And what that will do is it will automatically bend the item that we're placing that region in. So there you can see it's bent the flex board. Now, to make it a little bit easier in defining how long the flex needs to be, or kind of what the radiuses need to be, basically what you're trying to get to is a certain length on the flex, and you want to be able to see where the bends are going to be in relation to the item it's got to attach to make sure the shape of it's correct. Which is something that's hard, again, to do in the mechanical tool. So a PCB-centric application for doing flex design makes this job much simpler. But what I can do is I can bring in a model of the mechanical to make my job even easier. So we'll go up here and choose Import Mechanical Model, and then we'll select our step model that our mechanical engineer can generate for us. Just a couple seconds here to load in. And we can save it with the design so we can always easily come back and see it once it's been positioned with the design. I'm going to maximize this window real quick, and then we'll go back to that side by side. All right. So we can double click on this, guys, tell it what it is. It's a mechanical model. As you can see, we can bring in PCB models as well. So if I'm doing multiple PCB model or stacking of boards, I can bring in multiple PCBs and stack them. Or if I'm just interconnecting between two PCBs, I could use a PCB model to determine where it mounts and how to connect it with a flex or other connectors for that matter. So let's call this camera body lower half. Now I need to rotate this around to get it into the right position. Oops, that was right where I wanted it, right there. But I can use mating capabilities in PADS Professional to actually mate it to the surface and axis, so I don't have to sit here and try and position it by hand. So we do right-click, mate, and then I want to mate by axis. I'm going to choose that location right there, come down to the board, and choose that location. All right. And that will line it up for us. And it may have already picked the surface, actually. Nope. So now I need to mate the bottom edge of the board with the top edge of the board. So we'll do align face. So I want that face there. And then to easily pick the bottom one, I actually need to turn the mechanical model off real quick. And then pick that face there. All right. Now that should have moved it into position for us. Yep, so it's fully mated with the mechanical model with a couple clicks, just like you would in a mechanical engineering tool. So now I can go ahead and close that out. And just real quick, I can come down here and do add. If I want to be able to change the colors of this or dim it, like I can make it less bright if I want. I could change the color of it if I want, and things like that. All right. So next, the important thing here that we're trying to do is line up this board here with our buttons. All right. We can see the mechanical engineer at least put it in the right location for us from side to side, but now we have to adjust. Is this flex long enough to accommodate bending radiuses and such? All right. So we go back to our vertical view. I need another flex region. I'm not going to be able to do this with just one flex region bend area, more than likely. It's going to take 2. Sometimes it takes 3 in order to get the radiuses correct. And then again, I can adjust the proper parameters here. So we can leave that at 90. You can see it automatically bent it at 90 degrees for us because that was the defaults. But now I need to start playing or adjusting these angle or these radiuses here. We can control how far the bend is from the rigid area of the board. That is another constraint actually that you must follow. You have to have a certain distance from the rigid edge of the board to where the bend starts in order for it to not break or have assembly issues. All right, so as I continue to move this back, you'll see it'll end up dropping that down more and more. All right, so with a little bit of iterative process, we can get this perfectly lined up with where we need it to be in relation to the PCB. All right, so just after a couple minutes of playing around with some positioning and angles, we're able to get it perfectly lined up with our printed circuit board, verifying that our angles here are correct as we expect them to be. All right, when it's assembled. All right, now let's move on to some other flex bending dynamic verification capabilities that the tool provides. To do this, I'm going to open up our Hazard Explorer. Go ahead and mount that real quick here. And with this, with our online DRCs turned on, we have bend area verification. So what I can do here now is it will tell me if I have any issues related with the bend areas when I place components on the board, or if I'm routing and putting vias in, or traces. Like I mentioned earlier, traces can not be routed at 90 degrees within a bend area. So just as an example here, we'll take this flex, our camera one, and we'll put a bend area on it. All right, so there's our bend area. If I scroll over here to the flex and look at it, we can see there. Let's make this a little bit easier. Let's turn off the mechanical. All right, so there's our bend area. Obviously, if that was too tight of a bend area, we would get a hazard telling us that the bend area is too tight based on the thickness of the flex and whether it's dynamic or not based on our rules up there. So if we go to like 5, all right, and I deselect that, we'll see there's our violation popped up letting us know that our bend area is too abrupt for that area. All right, so this is part of the dynamic verification that the tool is going to do for you, and it's even shown an error marker here that mechanical tools don't do, and a lot of general PCB applications do not do for you. Okay, so another example here is, let's say I take a component and place it on the flex and relative to the bend area. The same thing would be if I'm routing and putting a via in. All right, so when we place our part on the board, this is another very important characteristic to pay attention to, is when I add the part to the board, it's going, or the flex region, it's automatically going to switch the pad stacks over to rounded corners from square. So this, you build this in to the part. There's special capabilities there. We can take a look at it just real quick. Go to libraries, pad stacks. Here's the pad that's being used for this part. You'll see there's a flex tab here, and I can define special geometry for the cover layer opening and the copper pads themselves. So the tool will automatically take care of the switching from square pads to rounded pads on a flex region for you automatically. And again, getting back to our real-time DRC functionality, if I pick up this part and move it into the bend region, you can see it won't let me put it there in that region. It automatically bounced it back because it knows I told it that I didn't want, or the DRCs automatically know you can't put parts in bend region. Now you can override that for those of you out there that are going to do flex. You can say allow certain things within a bend region, and it's defined by that region. But I can also put a tolerance on this. So if I don't even want anything close to it, I can say 25 thousandths. All right. Now, as you notice the area actually got bigger here. So now when I move the part within that region, it won't let me drop the component even close to that area based on the region. All right. So again, some of the powerful automation functionality that is available in a tool that is flex aware versus some of the basic CAD tools out there where you have to pay very close attention to that, or you're going to have quality issues when you get your product built in fabrication and assembly and in the field. All right, moving on to some routing. We're going to route this curved flex. So we have our connector placed already. To make it easy to route to the contour of a rounded surface like a flex, we're going to use the hug route function in Paths Professional. So we go to route, add route, hug route, and then we click on the pin that we want to route from. Click where you want to start the contour to follow, and then we'll cruise up here to the top. And then we'll click where we want it to end, and then you click on the side that you want it to show up on, and there it automatically throws in a trace the exact contour of the flex edge, eliminating tedious work of routing the rounded corners we need in flex and trying to follow a complex shape that your flex might be in the first place. And then to finish that trace, we can simply just click the multi-route. All right. And then, it's just a repetitive process from there on out doing the rest of them. But now we can use this trace actually as our guide for all these other traces. And then lastly, again, we want to be able to customize our plane shapes based on area, because in our flexes, we generally don't want solid copper. You want, especially ones that are going to bend at a fairly tight radius, you want to use hatch copper, because solid copper produces more stress on the flex. Any traces that are on the other side of it will end up with more stress on them, and they could be more likely to break over time with vibration or dynamic movement. All right, for our example here, I'm just going to, you don't have to get precise with plane areas. I don't have to create the exact overlay of this. If I wanted to, I could copy this shape, paste it down, and then repurpose it a plane area. But I'm going to keep it plain and simple here. So we're going to go to plane shapes. I'm just going to draw a rectangle right over the top of this, and you'll see it automatically fills it in. Okay, now by default, it's solid copper. All right. And you can specify any net name you want. You can click on mouse select and have it automatically, or have it click on a net that you want it tied to. But we're going to do plane class override, which means we're going to specify that I want this to be hatched, and then I can specify a hatch parameter for it and hit apply. Now there's a couple other little parameters here that are not allowing odd angled shapes where it automatically fills them in. This can help with fabrication to some extent for acid traps and such. But you can see very quickly, I've basically created a plane area. It's only going to fill in the copper inside of the board itself, or inside the board outline, or the route border, I should say. That's one of the handy features of the route border, and it's hatched based on my requirements. And for each one of my plane areas, I could go in and specify something completely different, or each area on the board, even for that matter. So my little button board up here, I could have something completely different than each one of these flex as necessary. All right, let's do a quick review of the 3D now that we've gone over most of the major functions in the end without having to do paper dolls. We can see how it's going to bend, the length that we need to make certain flex regions, the angles that we need to put on items can all be tested virtually prior to designing producing your first prototype, ensuring that your initial designs, without having to go through multiple prototypes, will be high quality and accurate to begin with. And to just do a quick recap, if you've never designed a flex circuit before, not only do you have to learn about the design requirements for flex, but it's also good to know what's required in a tool that'll make your life easier. Being able to do everything in 3D, having tools that have automation for design rules of bend areas, where things can be placed in bend areas, placing components in a flex circuit with it automatically being able to, replace the pad stacks for you, knowing that, I can only have a certain bend radius depending on the thickness of the flex, and having the tool automatically tell me whether or not I've met that requirement or not is all part of the automation behind using a PCB tool that is flex aware.